This conference will now be recorded.
Hello everyone. Basic character of amines, I mean aliphatic amines, that we have already discussed, and now we are going to see a question related to that, and after that there will be discussion related to aromatic amines. That means where benzene ring is directly attached to nitrogen and how we can prepare them and what are their specific reactions. All these things will be discussed. So this problem is related to basicity for amines. So in this question, you will find not only aliphatic amines but also aromatic amines, because for aromatic amines, basicity part also last class we have discussed. So now, as we know basic character of both types of amines, we can discuss this question. Here we have four compounds, phenyl methanamine. So the first compound is basically this structure PH, NH, then we have methyl group. Then the second structure, that is molecule B, NN dimethyl aniline. So aniline is pH ring and aniline pH ring attached to NH2. But if you replace 2H with 2 methyl group, now the name will be dimethyl aniline. Then what about C? The structure of C is, it is N-methyl aniline. That means you have only one amine. Fine. Then benzenamine. Now benzenamine means it is nothing but aniline molecule. Fine. Now we have to choose the correct order for the basic nature of the above amines. So as you can see here, it is already selected option 4. That means the first amine, phenyl methanamine, that should be maximum basic, right? Sorry, I have mistake. There is a mistake. It is not PHNHME. It is actually PHCH2 NH2. This is actually aliphatic amine. So here all the amines that you are seeing, first of all you have to recognize among them which one is aliphatic, which one is aromatic, because we know aliphatic amines are always more basic. Now this one is aliphatic in nature because here NH2 is not directly attached to pH ring. Fine. So PHCH2NH2, you can also call it benzyl amine because benzyl group is PHCH2. Benzyl amine. Okay, so PHCH2 NH2, look at these values. This is the pKb value, as you can see in this table, 4.70. Now come to the next structure, NN dimethyl. NN dimethyl means this one, 8.92. Just look at the values, then we will discuss why it is so. Then when you have only single substitution, that is only one H is replaced by Me, then the value is PHNHMe, which is 9.30, and if it is simply aniline, then it is 9.38. Now from the pKb values, as we know, when pKb value is increasing, that means basicity is decreasing. These two are inversely related to each other. So according to this should be maximum acidic. So this is molecule A. Then molecule B is this one. Molecule C is, and this is D. Okay, so among these only pH CH2NH2, this is aliphatic, and that is why it is most basic. And also we know when NH2 group, it is directly attached to pH ring, the lone pair that is present over nitrogen, that will take part in resonance with the double bonds of benzene ring, but in this case it is not directly attached, so no question of resonance, and that is why it is maximum basic. And after that we have aniline and its derivative. So if you consider the simple structure aniline, here lone pair over nitrogen, that will take part with the in resonance with the double bonds of benzene ring. Same thing will also occur for B and C, but remember in B and C you also have alkyl group. So here we have two alkyl group, here we have only one alkyl group. So with increase in alkyl group, because of its plus I effect, lone pair availability over nitrogen will increase. So that is the reason among these three, B, C, D, maximum basic will be B, then C, because now there is still one alkyl group, but in D there is no alkyl group, so no question of plus I effect, and that is why the order is A, B, C, D. So option 4 will be the correct option. Next problem. Here a heterocyclic molecule is given. Heterocyclic means, remember, it will be cyclic and some carbon atoms will be replaced by some heteroatom. It may be nitrogen, sulfur, oxygen. So in this case, as we are discussing amine, obviously nitrogen is there, and total 5 nitrogen atoms are present in this molecule, and that are marked by A, B, C, D, E. Now you have to find the favorable site, or it may be more than that, sites for protonation. Now it is another way of asking which nitrogen is maximum basic. That means in which nitrogen the lone pair availability is maximum. So that will be considered as most basic, or you can say that is the most favorable site for protonation, because protonation means it is showing basic character. Now it may be only one, it may be more than that, is or are, because in some options there is more than one, that is values you can see 1, 3 and 2, more than one, but option for only A. Now lone pair availability, if we want to know, basically we have to consider that resonance, whether it is present or not, because if it is present, that means lone pair availability over nitrogen, that will decrease, but if it is not present, it will increase, that means basicity will increase. So another way you can say, when resonance is high, then basicity is low. Now individually if we see here, NH2, which is attached to this benzene like ring, though it is not benzene ring, 2 nitrogens are there. Now here also lone pair over nitrogen, it can take part in resonance. So after resonance, the structure will be something like this. Now NH2, this nitrogen is positive. This part I am not drawing, because I am drawing only the part which is involved in resonance. So now there is nitrogen and negative charge over nitrogen, and rest of the part there is no change, though further resonance also you can do, but important point is here resonance is present, so lone pair availability is less, so obviously A will not be very favorable site. Similarly, if we consider the next one, which is B, now see, in case of B you cannot find any resonance. If you want to do it forcefully, that is, if you consider this lone pair, and why not, because that will that is not possible, because if you want to do this, what structure you will get? You will get something like this. I am drawing only the right hand side part, because that is the part where we are doing the discussion. So there is already double bond, but if you still want to make another double bond, it will be something like this, which is not at all possible, because tetravalency in this way, which is not linear, nitrogen is not linear, in this way it is not possible. So here for B resonance not possible, in A it is possible. Now come to C, same thing is also for C. If you want to do some resonance, there will be total 4 bonds surrounding nitrogen, which is not possible. So in C also resonance not possible, lone pair availability is high. The next part site is D. Now we will focus on the left hand side part. Now, if you want to do resonance in D, see what you will get. You will get something like this, but that is not possible. Again, 4 bonds surrounding nitrogen, which is not possible. So in D also resonance not possible. And what about E? Yes, in E it is possible. How it is possible? See, just focus on the left hand side part. But there is no double bond. Double bond is here. Now if we want to do resonance, now it is possible. So what structure you will get? You will get double bond here. Now nitrogen is positively charged. It is already, hydrogen is there, and negative charge over this nitrogen. So in case of E, resonance is possible. So out of A, B, C, D, E, only in case of B, C, D, resonance not possible. That means this will be the ideal site for protonation. That is the favorable site. So correct option according to this logic, it should be option 2, that is B, C, D. Fine. Now after discussion of this question related to basicity of amines, next we are starting What are the different methods by which you can make aromatic amine in H2 group directly attached to benzene ring? After this, there will be chemical reactions of aromatic amines. The first method that we are going to see is from chlorobenzene. That means chlorine directly attached to benzene ring. This is the starting material. And what we are doing for insertion of NH2 group, we are heating it with alcoholic ammonia, not aqueous, alcoholic ammonia. And here we have also used cuprous oxide, Cu2O, copper plus 1 state, and temperature is 200 degrees centigrade. So we are getting aniline. Starting material chlorobenzene, product is aniline. If starting material is phenol, that is also possible. Now phenol is reacting again with ammonia, but temperature compared to the previous equation, now it is very, very high. And you are also using anhydrous zinc chloride. Fine. And we are getting aniline. So this is the second method by which also aniline can be produced. Now this method we have already seen in case of aliphatic amines, which is also known as Hofmann bromamide degradation reaction. Why we call it degradation? Because in this case one carbon atom is lost. Which carbon atom lost? Carbonyl carbon. So in this case starting material is basically amide, but in this case it is written benzamide because benzene ring is directly attached to amide group. So starting material is benzamide and final compound is basically 1 degree amine. That is actually in general, if you consider Hofmann bromamide reaction, it is preparation of 1 degree amine, primary amine starting from amide. But as we are doing the discussion which is restricted to aromatic amine, so that is why you have to take some aromatic amide. Otherwise, how we will get aromatic amine? So that is why benzamide is the starting material and final product is aniline, which is aromatic amine. And the reagent is same, that is Br2 in presence of basic medium NaOH or KOH, and this CO is lost, so that is why it is degradation, and aniline is produced. These are the byproducts. Fourth method, now the starting material is nitrobenzene. So see, here already nitrogen atom is present, so what we have to do, we have to use some reducing agent, NO2 group reduced to NH2. So you don't need to use any ammonia like this type of reagent because nitrogen is already present, and this N will be the N of NH2. Now what reducing agent you can use? You can use hydrogen gas in presence of finely divided in nickel, palladium, platinum. So this type of reagent we also use for any hydrogenation reaction, right? So same thing. You can also use these metals, that is tin, iron, Zn, but in acidic medium. In the second method, we are not using any hydrogen gas. The first method, you can use hydrogen gas. The second method, we are using tin, Zn or Fe. In presence of acidic medium, we have taken hydrochloric acid. So these are the four methods by which you can prepare aniline. Next method actually all the methods are discussed for preparation. Next is chemical properties of aromatic amines. Now under chemical properties of aromatic amines, you will see several reactions are there. So we have numbered all these reactions one by one, we will discuss. The first one is alkylation. Now alkylation we have also seen when we have discussed chemical properties of aliphatic amines. Same thing also you can see here. We are calling this name alkylation because some alkyl group will be inserted by replacing the hydrogen of NH2 group. So that is why the name is alkylation. In this case, you can prepare secondary aromatic amine or tertiary aromatic amine, even quaternary ammonium salt, starting from the primary amine, which is aniline, the simplest aromatic amine possible. And for the source of alkyl group, we have taken methyl chloride. So here it is written less amount of CH3Cl, because if you are taking excess amount of CH3Cl, then another H will also be replaced by another methyl group, and in this case you will be ending up with PHNMe2 molecule. But if your purpose is to make PHNHMe, that is 2 degree amine, secondary aromatic amine, then you have to use CH3Cl less amount. Actually you have to use 1:1 amount, because per molecule of aniline you just need one CH3Cl if you want to make secondary aromatic amine. So the final product, whether it will be secondary amine or it will be 3-degree amine or it will be quaternary amine, that depends on what is the mole ratio of aniline and also alkyl halide. So in this case, if you use 1:1, obviously you will be ending up with 2-degree amine. But if you take further 1 mole, it will be 3-degree. So see here we have taken aniline and excess CH3Cl. Now we are getting 3-degree dimethyl aniline, and you are using again another mole of CH3Cl. Now already trivalency of nitrogen is reached, and if you are doing adding another CH3Cl, now the lone pair of one nitrogen, it will attack here, Cl will be removed, and as there are total 4 bonds surrounding nitrogen, so that is why there is a positive charge, and this is called quaternary ammonium salt. Now the second reaction that is possible is acylation. Acylation means you will insert this type of group. So H will be replaced by H will be replaced by COR group. Now for the source of C double bond OR, you can use either acetic anhydride or you can also use acid chloride. So in this case, which acetic anhydride we have taken? We have taken the anhydride that you get from acetic acid. 2 molecules of acetic acid. If you remove water molecule, you will be getting this anhydride. If you want to see the structure, it is something like this. COCH3 2 times, and in the middle there is oxygen. So this is the source of COCH3 group. This group will be replacing this H, and you will be getting NHCOCH3, and this reaction is acylation. In the previous case, H is replaced by alkyl group, but now it is replaced by COR group. That is the difference. If you take acid chloride, in this case we have taken acetyl chloride, which is the chloride you generate from acetic acid, that is replace the OH group of acetic acid, you get CH3COCl, and this is the reagent that you use. So here the byproduct will be basically this part will be the byproduct CH3CO2 minus. Now this will take this H, so you can write it as if it is acetic acid. So that is why we use pyridine base, which is not very strong, but it is basic more or less, and it is enough as basic so that it can consume this byproduct, and in the second case byproduct is HCl. So when the byproduct is removed in from the medium, what will happen? Now the equilibrium will be shifted from left hand side to right hand side according to Le Chatelier's principle. So that is the reason why we have used pyridine in this case. It helps to remove the byproduct and resulting in increase of the actual product formation. So this PHNH-COCH3, this molecule is called acetanilide. Fine. Come to the third reaction. Now this is just like acylation, but the name is different. Now we are calling it benzoylation. In the previous case, you have inserted COR group, where this R group is alkyl group. But suppose if this R group is pH group or any substituted pH, I mean AR, then the name is different. And here the reagent that we are using for this purpose is benzoyl chloride. That means chloride of benzoic acid, PHCOCl. And the same thing, this group will be inserted replacing one H, and as a result now you get PHNH-COPH. So this is the group which is inserted by replacing H, and this is called benzanilide. Remember in the previous slide we have seen the name of the product acetanilide, where it is COCH3 group. Now it is COPH group and the name is benzanilide. Carbylamine reaction is also possible with primary aromatic amine, which is aniline. So carbylamine reaction we have seen in case of aliphatic amines, and it is only for 1-degree amine. So it is so specific for 1-degree amine that you can use this test as identification test for 1-degree amine. Suppose you have any amine sample and you do not know whether it is 1 degree, 2 degree or 3 degree, you can do this test, which will help you to prove yes, it is 1 degree, because only from 1 degree amine you get this type of product, which is in general you can write as RNC, but in our case our group is pH, so this is the structure PHNC. Normally you can also write it like this, but if you want to write the bonds clearly, it is N positive, then triple bond C minus. So this is phenyl isocyanate, and these are the byproducts. So this molecule is basically responsible for the bad smell, and which is the characteristic smell from which you can understand that this is 1 degree amine. Fine. Number 4, mustard oil reaction. Now mustard oil reaction also we have already seen in case of aliphatic amines. So same type of reagent we will use again. So when we are treating aniline with CH2, carbon disulfide, or heated together, that is if you are treating it with CH2 or you are heating it with CH2, what will be formed? S-diphenyl thiourea will be formed. Now when it is simple urea, the structure is NH2CONH2. But when you are saying thiourea, now see, this is the structure of urea, NH2CONH2. Now when I am saying thiourea, that means this oxygen, now it will be sulfur. And see, both this H, as if you have replaced with 2 phenyl group. So that is by the name S-diphenyl thiourea. Okay. And in this case, 2 molecules of aniline, 1 molecule of CH2 is heated together, H2S is removed, and as if this H is that is 2H, now they are connected by this CS. Fine. And finally, if we treat it with strong HCl, phenyl isothiocyanate, that is PHNCS. Remember, thiocyanate is HCl, where S is connected to the group, but in this case N is connected to the group in that is with which we are dealing with. So that is why it is isothiocyanate, and this molecule is basically responsible for the pungent odor, which is just like mustard oil, and that is why the name of this reaction is mustard oil reaction. Fine. Smell of mustard oil, so that is why the name is such. Number 6, reaction with HNO2. But remember, nitrous acid we do not use directly because this acid is not very stable molecule. So if you want to make HNO2, we take mixture of HCl plus NaNO2. So when you use this mixture, what happens? This Na is replaced by H, but remember this is produced in situ. I mean, you are not making it, adding it specifically from outside. You are just adding the mixture HCl NaNO2, and in the medium HNO2 will be produced, which is the actual reagent, and it is called nitrous acid. In case of aliphatic amines, we have seen that 1 degree, 2 degree, 3 degree aliphatic amines, they behave differently with nitrous acid. And in this case also we will see something else will happen. That is when it is aromatic amine, how it is reacting with HNO2. This reaction occurs at very low temperature. 273 to 278 Kelvin means it is 0 to 5 degrees centigrade. First, there is formation of diazonium salt. Now, this diazonium salt is stable for a very short time, provided you are maintaining the low temperature. If somehow the temperature is greater than 5, this may be decomposed. Okay, so that is why you have to maintain low temperature. And don't think that low temperature also it is stable for a long time. No, that is also stable for some time. So this diazonium salt that is produced, it is diazotization. It is called diazotization, as if you are diazotizing aniline by the treatment of HNO2. But HNO2 you are not directly using, you are using mixture of HCl and NaNO2. Now this diazonium salt, though it is unstable, so you cannot consider it as if it is a final product. But remember, this diazonium salt can be the source of so many other variety of aromatic compounds. So that is why it is so much important. So these diazonium salt are very important class of compounds that are used for the synthesis of variety of aromatic compounds. So what we do when we do this reaction and you get this diazonium salt, we do not isolate it because it is not possible, it is very unstable. In the same reaction medium, we just add the next reagent, which is required for the production of variety of aromatic compounds. Look at this example. Aniline is treated with this mixture, which is the source of HNO2. Temperature very low. So what you are getting? You are getting this salt. Why we are calling it salt? Because there is positive charge, negative charge, electrostatic interaction, and full structure if you draw, it will be like this: N triple bond N. Now this N is positively charged because total 4 bonds are there, and this positive charge is balanced by the counter ion Cl minus. This counter ion is coming from HCl. Now this is the structure that you are getting here, but general structure you can consider as if it is pH N2 plus X minus. So I am calling this Cl as if it is X because this X may be different groups. In this case it is Cl because you have taken HCl, but other counter ions also possible. So in this way we make the diazonium salt, but remember this is not very stable. It is stable only for some time and also at a very low temperature. Now next, though this is not the last reaction, that is we are discussing chemical properties, this is number 6. After this there is number 7 also, but in between 6 and 7 we will elaborate this part, that is diazonium salt part, because from synthetic point of view this is very important. It can be the source of so many other aromatic compounds which you cannot prepare under normal condition, but by this diazonium salt you can easily prepare them, and that is why this salt is so much important. So what is diazonium salt? If we ask this question, this is the general formula: Rn2 plus X minus. So these are basically aryl group, that is pH ring or substituted pH ring, and X may be Cl minus, which you have already seen, but it may be other negative anions also. Now if it is primary aliphatic amine, remember the reactions that we have discussed, then alkyl diazonium salts are produced because it will be alkyl. In this case it is aryl, but when it is aliphatic amine it will be alkyl diazonium salt. So alkyl diazonium salt, if you consider, and the diazonium salt that you are getting from primary aromatic amine, if you compare their stability, obviously the salt that you are getting from primary aromatic amine, they are comparatively more stable, but don't think they are very stable. I'm saying comparatively more stable only for a short time, that is also in solution, and also very low temperature 0 to 5. So you have to maintain this condition, and that is the reason it is used immediately after preparation. So suppose this is produced and it is present in test tube, so what we do, we do not isolate it, the next reagent is added to it so that we can get some other compound. Fine. Now these are some examples of different types of diazonium salt. This you have already seen. Look at the name also, benzene diazonium chloride, because this is benzene, then diazonium part, then chloride. But suppose you have some substituted benzene ring, for example 4-methyl substituted benzene, so it is actually toluene. So that is why para-toluene diazonium, this is diazonium, but this ion is now hydrogen sulfate, so that is why the name is different. Then the third molecule, now it is nitro substituted, 4 position. So para-nitrobenzene, then diazonium, then chloride. So in this way names will be different, and you can see different types are also possible for diazonium, though the most common salt that we will mostly discuss is the first one, benzene diazonium chloride. Now if we see this, that is resonance that is possible in diazonium salt. So this is the cationic part, just remove the anionic part, focus on the cationic part. What type of resonance is possible here? The double bonds of benzene ring, it can take part in resonance. So see, now there is positive charge. This N is still positive because there is total 4 bonds, though actually it should be written like this, because when there are total 4 bonds, you cannot write it as if these 2 bonds are 90 degrees to each other. It should be written like this, but for simplicity it is written in this way. And then further resonance structures are also possible. Okay, so these are the resonating structure of benzene diazonium salt. Fine. Now, the stability of arene diazonium salt compared to alkyl diazonium salt, as we have already mentioned in the previous slide, it is comparatively more stable. I am not saying it is very stable. It is also unstable, but comparatively more stable, and that is because of this type of resonance possible in arene diazonium salt, which you cannot have in alkyl diazonium salt. So here the positive charge is dispersed in the whole aromatic ring. So when there is more dispersal of charge, obviously the system will be more stable. So these salts are colorless, crystalline solid, and they are very soluble in water. So if it is cold water, then there is no reaction. It is simply soluble. But if you heat it, now there will be some reaction with water also. That is possible. Then another diazonium salt, which is also used for synthetic purpose, benzene diazonium fluoroborate. What is the structure? This is the structure. pH N2 plus, anion is BF4 minus, fluoroborate. This is not soluble in water, and this is quite stable at room temperature. So this is the only specific exception, that is you can better you remember it. If it is asked among different diazonium salt, which diazonium salt is comparatively more stable and not soluble in water, so its property is different, not like other diazonium salts. So that is why specifically this molecule is, its structure is shown here. It is not soluble in water, and room temperature stability is also there. Okay, now we will focus on the chemical reactions of diazonium salt. Remember, we are discussing chemical reactions of aromatic amines, but under that, now we are focusing mainly on diazonium salt, which is basically the product of diazotization of aniline. Okay, so chemical reactions of diazonium salt, two types possible. The first type is where the diazonium part, I mean the N2 group, that is remove itself. So it is replacement of nitrogen. So that is a type of reaction, and most of the reactions is will be under this category. But another type is also there, which is retention of diazo group. So other reactions are diazo group, that is N triple bond N part, that will be retained, but some reaction will also occur. So that is the difference. So the first type we have here, reactions involving replacement of nitrogen. Now under number 1 category, the first one is, if we replace this N2 part, that is the diazo part, by hydrogen, then what will happen? We have to use some reducing agent, not very strong reducing, mild reducing, like hypophosphorus acid or phosphenic acid. You can also use ethanol. In presence of cuprous ion, it gives benzene. So this reaction proceeds through Federical chain mechanism, but we are not going into details of mechanism. So see, this is the diazonium, benzene diazonium chloride in presence of H3PO2, or you can take ethanol. So see here, N2 is replaced by H. So basically you are getting back benzene. But if there is some substitution present at any position, it will be some derivative of H. Okay, this is the first reaction, N2 replaced by H. So this is basically replacement of N. So mostly the reactions will be replacement by different groups. Replacement by chloride, bromide, or cyanide. Remember, here we do not have fluorine or iodine. I mean fluoride or iodide, only Cl and Br. And under this category, the first type is Sandmeyer reaction. When you are mixing diazonium chloride salt with this type of reagent, look at this reagent, it is CuX. You can also write it as Cu2X, but basically it is CuX where oxidation state is +1. So CuX where X is Cl or Br, or it may be Cn. So when it is chloride, that is I mean chloride and bromide, you are taking the combination CuX, HCl or HBr depending on your requirement. But when it is Cn, you are taking the salt potassium cyanide. So what we are getting? Chlorobenzene, bromobenzene or cyanobenzene. Fine. So this is known as Sandmark reaction. And see, in all cases N2 is removed because we are replacing the diazo part. Under replacement of by ClBr we have another method which is Gutterman. You can find some similarity, but they are not exactly same. So under Gutterman, basically you can prepare only chloro and bromobenzene, and now the reagent is different. In the previous case, you have taken CuHHX, but now you have taken only copper and the corresponding acid. So we are getting chlorobenzene, bromobenzene. The yield in Sandmark reaction is found to be better than Gutterman. Okay, so mostly we use Sandmark because of this advantage. So this is number B. Next will be number C. Now, if you want to get iodine in benzene, what you will use? You have to use potassium iodide. So it is simply the salt is heated with potassium iodide and this N2 is replaced by I. N2 is removed. This is the byproduct. D. Now the starting material is something else. Here the counter ion is Bf4 minus. Fine. And in this case, first we will see D, which is basically this one. So what you are making? You are making fluorobenzene. This reaction has a specific name, Barnes-Schumann reaction, or simply called Schumann reaction. For benzene diazonium, sorry, it will be fluoroborate, is treated with, okay, sorry, it is mentioned in this way. Basically, benzene diazonium fluoroborate that you can prepare starting from pH N2 plus Cl minus. So suppose you have taken, so this is the diazonium salt we mostly deal with. If you are treating with HbF4, then in the medium the Cl minus will be replaced by Bf4 minus, and this is the starting material for Schumann reaction. So in Schumann reaction, you just have to simply heat it. You don't have to use any reagent. And this F is basically coming from BF4. And another reaction, if we want to get NO2 group by replacing N2, now you have to heat this diazonium tetrafluoroborate salt by sodium nitrate. So this is the source of NO2 group. So this is the next reaction, which is replacement by NO2 group. This is basically replacement by fluorine. I mean the Schumann reaction. So remember, these reactions, why are they so much important? When you directly want to insert fluorine in benzene ring, it is really difficult. And the process that we use, that is if you want to use fluorine directly, fluorine gas, this is really difficult because fluorine is very reactive. So many other undesired compounds will be formed. But if you really want to get only fluorobenzene with high yield, this method is better. So that is the importance of diazonium salt. Though this salt itself is not very stable, but if you can use it properly, you can find so many applications. So nitrobenzene we can produce when we are heating the fluoroborate salt with copper and sodium nitrate solution. Fine. So 5 replacement reactions we have seen: A, B, C, D, E. It will be A. Replacement by HO group. Now in this case, you are simply heating with water. That's it. Remember, benzene diazonium chloride, it is soluble in water if you can maintain the temperature low. But if you are heating it, immediately there will be replacement by N2 plus group with OH. And that is why low temperature maintenance in when it is in solution, that is very important, because if somehow the temperature is increased, you will be ending up with phenol. If you do not want to get it, if you want to get it, you are deliberately heating, that is fine. But if you want to stick to this salt, then you have to maintain the cold temperature condition. So here it is added slowly to a large volume of boiling water and we get phenol. So this is next, that is G, replacement by aryl group. This reaction is known as Gomberg reaction. In this case, again we have taken this salt, we are simply heating it with benzene, and you have to do it in presence of NaOH. And why? Because here the byproduct is this Cl and H together, HCl. So this HCl must be consumed by this NaOH. So that equilibrium is shifted from left to right, and that is why basic medium is necessary. So what we are getting? We are getting biphenyl system, two phenyl ring connected to each other. This is the byproduct, nitrogen gas. The next reaction, it is actually H. Replacement by carboxylic acid group. So see, this is so versatile. Even you can insert some CO2H group. And what will be the source of CO2H group? You can take acetic acid. Suppose you want to insert CO2H. So you have taken CH3COH, and here the starting material is the fluoroborate salt, which you can prepare starting from benzene diazonium chloride. So here this N2 is replaced by CO2H group, and BF4 minus, now it is BF3, and this extra F, now it is with this alkyl group of acetic acid. So these are the byproducts, but the important point is what you are mainly producing here. Starting from this salt, you are producing benzoic acid. So the CO2H part, that is coming from acetic acid. So now we have finished the first category. The first category is basically where you have replaced the N triple bond N part, I mean the N2 plus part, or you can say the diazo group. But now the two reactions basically that we are going to discuss here, we are not replacing the N part, I mean the NN triple bond part, but we are going to retain it. But still there will be some reactions in the other part of the molecule. But remember, two nitrogen will be there. It will not be removed in the form of nitrogen. In all the previous reactions you have seen, always N2 gas, that is the diatomic nitrogen gas, is produced as a byproduct. But now that will be not the case. The first method under this category, reduction to hydrazine. Hydrazine, if you simply write, it is basically this molecule N2H4. But when I'm saying it is phenyl hydrazine, as if, sorry, it is N2H4. You can also draw the structure like this. But suppose one of the H of N2H4 you are replacing with pH. Now the structure will be like this: pH NH NH2. So pH NH NH2 is the final product here. So basically we are reducing the N triple bond N. Now there is no double bond or triple bond. What reducing agent you can use? You can use zinc dust in presence of acetic acid. You can use SnCl2 in place of hydrochloric acid. Then sodium sulfide can also be used. Na2SO3, that is sodium sulfite. You can use sodium hydrosulfide, that is NaHSO3. So instead of taking Na2SO3, you can also use NaHSO3. But the final product is now NN triple bond part, 3 hydrogens are inserted. So finally we are getting pH NH NH2. The second one is very important from because this test is normally used for identification purpose. Okay, first let's see what is this reaction. Aryl diazonium ion, now it will behave as if it is electrophile. Remember, there is positive charge, so it will prefer attack by some electron rich species. That means it will prefer attack by nucleophile. So it is itself behaving as electrophile. Okay, aryl diazonium ion is now electrophile and it will couple with some nucleophile. That is why the name azo coupled. So another interesting feature of this aryl diazonium salt is their electrophilicity. Okay, the positively charged nitrogen makes them susceptible to nucleophilic attack of any activated aromatic ring. So the nucleophile that are going to attack, they are also some aromatic ring, but remember they are activated aromatic ring. Now when we say activated aromatic ring, there will be some group attached to benzene ring. Now this group, it will be suppose OH, that is phenol. It may be alkoxy, that is OR group. For example, OCH3, OET, that is O-ethyl. or it may be N-alkyl aniline. That means it may be any group like NEET. So all these are very donating group. So this part can be used as nucleophile and it will attack the aryl diazonium ion. So this is the reaction. Here we have taken NN-dimethyl aniline, that means PHNMe2. So this ring is highly activated because there are two methyl groups. They are having some plus I effect. Okay. Now this lone pair, suppose if it is taking part in resonance, now there will be negative charge density at para position, and this negative charge it can attack at this nitrogen, that is the terminal nitrogen, and now this middle that is another nitrogen, it is becoming neutral. But in this method step, aromaticity of N-dimethyl aniline is lost. So to regain the aromaticity, this counter ion, now it is accepting this H. So there will be again formation of double bond in this position, and now it is again aromatic. So see, now between two benzene ring there is some azo linkage. So that is why the name is azo coupling, and the name is para-N-dimethyl amino, para-N-dimethyl amino, then azo, then benzene. So this type of molecule you have to take, where X, do not think it is halogen, it is basically OH or OR, that is OMe, OET, like this. It may be aniline or it may be NR2 or even NHR. So this is the mechanism. Final product, where we have N double bond N both side, there is benzene or benzene derivative. So this product of this reaction is called azo compound, and it is also called azo dye. Why it is called azo dye? Because see, here there is conjugation, extended conjugation is present. This benzene ring, then there is double bond, then again another benzene ring. So even the double bonds of the first benzene ring, through this NN double bond, it can reach to the other benzene ring. So that is actually resonance, and because of this extended conjugation, they are always very colorful. Different types of color may be present, that is intense visible colors, and that is the reason they can be, their important, one important application is they can be used as dye. Fine. Now, as I have said, this test is very important from identification test point of view. So suppose you have any sample, you want to confirm whether it is aromatic or not, and primary aromatic amine or not. So what you can do, first you have to make this diazonium salt. So suppose you have any sample, you do not know whether there is NH2 group attached to benzene or not, but you can add NaNO to HCl. If it is present, there will be formation of diazonium salt. Now this diazo compound, it will couple with phenol. Now not just normal phenol, basically we take beta naphthol for this purpose, because when you take beta naphthol, there are two benzene rings. So now this extended conjugation, it will be further enhanced. So that is why color will be very good. So that is why beta naphthol or 2-naphthol is taken. This is position 1, this is position 2. So in this case also, this ortho position, I mean with respect to H, this is the ortho position, this position is highly activated. So that is why the attack is occurring through this position. You can also consider resonance like this. So see, negative charge density is very high at this position, which will attack here. So that is why this CN bond is produced. So this is azo dye. If you write this pH ring elaborately, you can have so many resonance structure. Conjugation is possible in extended way. So that is why the color is very intense. And from this intense color, which is basically orange azo dye, insoluble in water. So as it is insoluble in water, even you can get some PPT like form, right? Precipitate. So from this precipitate having intense orange color, you can easily understand, yes, that this amine is present. Similarly, you can also do another thing. Suppose if you do not know whether beta naphthol is present or not, if you want to confirm it, then this will be your unknown sample, and you can use in that case benzene diazonium chloride. So vice versa, either the amine part is unknown, then it will be the sample. If the beta naphthol part is unknown, it will be the sample. Fine. So in this case, HCl is byproduct, so that is why we are using basic condition so that it can consume the byproduct. So this is azodye test. In azodye test, instead of taking beta naphthol, you can also take any activated ring also. Though mostly when you want to confirm whether primary aromatic amine, that means aniline or aniline derivative present or not, mostly we take beta naphthol. But for example, if this part is unknown, that is, if you want to check whether there is any activated aromatic ring present or not, then the reverse test also you can do, but the aniline part is known and this part will be unknown, and in this unknown part you can take any activated ring. For example, you can see in this pink box all the possibilities. It may be any NH2 substituted benzene ring or naphthalene ring, or NR2 group substituted benzene or naphthalene, like this. So this is azodye test. So now if we summarize the importance of diazonium salt, they play essential role in industrial as well as synthetic organic chemistry. So for industrial, you can say, you have already seen how we can make some dye with so many different colors possible, and that is the reason they are employed in pigment and dye industries, primarily in producing colored fabrics. And if you consider synthetic organic chemistry, we have seen so many different types of reactions, mainly those reactions where you have replaced N2 group with H, OH, halogen, cyano, like this. So these are the, that is synthetic point of view, very important application, because some molecules, for example fluorobenzene, you cannot make by other methods, which is really difficult, but in this way you can easily make it. So that is, it is written, in some cases substituted aromatic compounds cannot be generated by direct substitution in benzene or substituted benzene, and that is the reason now we are making all these compounds via diazonium salt. Via means, first you take aniline or derivative, you make the diazonium salt, which is not very stable, and immediately you have to do the next step. If you want to get fluoro substituted, bromo substituted benzene ring, or any of these groups that are attached to aromatic ring. Fine. So these are the applications or importance of diazonium salt. That is why we have discussed it in a so elaborate way. So this is this started with number 6 reaction under the heading of chemical reaction of aromatic amine. Number 6 reaction, which is reaction with HNO2, and under HNO2 we have all this discussion. Now number 7 reaction for aromatic amine is electrophilic substitution. So when it is electrophilic substitution, we are saying that means here aniline itself, okay, that will let me first show you this resonance. In aniline, this type of resonance is possible, that we have already seen. So when NH2 is directly present, and which is basically the reason why its lone pair availability is low, basicity is very low. So then we have already seen this type of resonance. But here our purpose for this resonance structure is to show you that now if you look carefully in the resonating structure, now the electron density is high at ortho and para position. So this is ortho position, then this is para, another ortho position. So you will never find negative charge in the meta position. It is always at ortho and para position. So that is the reason now it can behave as nucleophile, as if this is a nucleophile ortho position, this is a nucleophile, this is a nucleophile. Now if it is nucleophile and if there is any E plus present, E plus means electrophile, so obviously there will be some interaction, and this type of interaction of benzene ring where there is some electrophile coming and aromatic ring itself is acting as nucleophile, then that reaction is called electrophilic substitution. So why we are calling electrophilic substitution? Because any of this H at ortho and para position with respect to NH2, that will be now replaced by the electrophile. So under this category, we will see 3 different reactions. So you can consider this picture as if it is the, that is if we summarize all this resonance structure, you can find this is the average resonance structure where negative charge density present at ortho and para position, and that is why electrophile is attracted towards this position. Fine. So the first reaction under this electrophilic substitution is nitration. For nitration, normally we use mixture of concentrated HNO3 H2SO4, and in this case we are getting para, ortho as well as meta. Now you may ask why we are getting meta, because according to the previous resonance structure we should get ortho and meta para only, because negative charge density is present at ortho and para. But what happens here, as you are doing the reaction in presence of acidic medium, there will be formation of anilinium ion. Anilinium ion is this ion, where NH2 is protonated. So I am writing NH3. This is positive. Now once it is positive, its electron donating capacity is totally lost. Now it is behaving as if it is electron withdrawing. And we know when it is withdrawing group, then obviously that is the resonance, that will also be not possible. So you can expect now meta substitution product. So here this is the percentage, or these two are almost 1:1, 51, 47, and ortho is very low, and the reason for its low yield is steric problem. So these two groups contact, though it is ortho position, from electrical point of view it should have good yield, but as it is, there will be some steric problem, so the yield is very low. In this case, if we see this description, direct nitration of aniline to give ortho and para-nitroaniline along with dark colored tarts. So there will be some other, because this method is not very good, because you are getting 1:1 product and there are some other undesired product, because HNO3 is strong oxidizing agent and aniline is itself very good in nucleophile because of its activated ring. So that is why you have to do this reaction under controlled condition. Look, the temperature is very low. It must be controlled condition. It should not be high temperature. So if you can do it under control condition, then you can get para and meta nitroaniline. But remember, here orthonitroaniline, its yield almost nil. So mainly the products are para and meta nitroaniline. Some more chemical properties we'll see in the next class. Today we are ending here. Thank you for listening.